Hello students, welcome back. We constructed up to real numbers. And that was this equivalence relation. Alright, now let's go to complex numbers. And this one does not require equivalence relation as a matter of fact. Just any pair of real numbers and define new algebraic operations, and that's it. You define addition like this. Just add up the x-coordinate and y-coordinate. Multiplication a little bit more cleverly, and then re-express a comma b as a plus bi. So how does the operation work? Well, addition is pretty simple. Just add up the first coordinate, second coordinate. Same as this. Multiplication is a little bit more complicated. You have to follow it. AC minus BD, comma, AD plus BC. If you do that, you get this, which is the same as this traditional computation. You can prove that this traditional computation and this one always turn out to be the same. And then we can identify each real number as x comma 0, or equivalently x plus 0i. And then, by the way, this number I is actually 0 comma 1, and it satisfies this property, which we call an imaginary number. Okay, we are up to complex numbers. Now, what if we have to go further? Luckily, we don't have to go further. It turns out the set of complex numbers is algebraically closed. So there is no arithmetic reason to extend any further. What do you mean by algebraically closed? Any equation with complex coefficient have roots inside complex numbers only. You see, if you set up a polynomial equation in natural numbers, you have to go outside. So you have to get integers. If you set up an algebraic equation in set of integers, you may have to go outside rational numbers. From rational numbers, for algebraic equation, quadratic or higher, then you may have something outside. So we have real numbers, complex numbers for square root of negative something. For complex numbers, not just quadratic or even cubic, arbitrary polynomial equation has solution in C only, so there's no reason to extend it any further. And this thing is called the fundamental theorem of algebra. I'm not going to try to prove it here in this course, of course. Let's see, alternative expression is here. So theoretically, we can consider some algebraic structure outside complex number system, which is more extensive, such as quaternions and octonions and things like those. There are many, but we do not call them numbers anymore. Complex numbers, that's the end, because that's algebraically closed, and then there is no arithmetic reason to extend any further. So that's the end. We got to the end. All the numbers done. All the construction done. But that's not the end of all the properties of numbers, I'm afraid. You see, how about some arithmetic properties? Addition, multiplication, subtraction, and division, those kind of things. Let's talk about those. We know how those were built for whole numbers. It's just basically a repetition of successor operation, remember? Repeated successor is addition, repeated addition is multiplication, repeated multiplication is power operation, and then we can consider the inversion, subtraction, division, and radical respectively. How about Z? Addition, multiplication, and power we can define like this. Addition, a minus b plus c minus d as sum that a plus c and b plus d like that. So that's a whole number. That's a whole number. And this whole number minus that whole number, that's an equivalence class. And multiplication, again, as a whole number minus whole number. There are a couple of questions here. Is this well defined? In other words, if I use different representatives, do I get different results, or are they always the same? As a matter of fact, we have to prove that. The proof is elementary but extremely tedious. I just wrote down the simplest version, but here, oh, it's this long. And this one, I didn't bother. To tell the truth, I've never done it before, and I never will. I don't think any of you will do these either. Maybe when you have to teach, you may do the very easiest one for demonstration and do exactly the same thing as I did. Everything is elementary but tedious, so let's just move on. And your students will do the same. In Q, we can define like this, using the common denominator. And then multiply the numerator and multiply the denominator, same way. So well defined, yes, because we have integer over integer. Integer over integer, yeah. We have appropriate structure of those, what do you call, the equivalence relation, equivalence classes. As for well-defined, well, even if we take different representatives to get the same result, we have to prove that. The proof is elementary, but extremely tedious. How about R? Well, this proof is actually not too bad. You can use a limit rule. Proving the limit rule may be hard, but you can use a limit rule, so it'll turn out to be okay, as a matter of fact. You can just add up the sequences and multiply the sequences. And in C, algebraic operation or arithmetic operation, addition, subtraction, multiplication, division, those are built in when we constructed C. So yeah, they are built in. So you don't have to worry about those. So in short, all the arithmetic operations, addition, subtraction, multiplication, division, they're all well defined, and also power operations as well. Just repetition is multiplication, so it's good. Now radical is a little bit different story, but yeah, in complex numbers, radicals are okay too. Now, how about some order properties? Get on with those, so let's de-emphasize again. W is well ordered. We define W using the recursive method. And we define like this, remember? And because the construction itself is next one, next one, next one like that, so we always have to have minimum whenever we have the non-empty subset. You see, that's the structure. So no matter what subset I select, the leftmost one, the smallest one, always exists uniquely. Z is well ordered, but it's not well ordered, but it is linearly ordered. Yeah, that's true. But any bounded subset of Z is well ordered, either forward or also reverse. You can extend the ordering A less than B like this. B minus A belongs to the natural numbers 1, 2, 3, 4, and so on. Here, I didn't want to use Z plus because we are talking about getting the structure in Z and then using Z again. It felt awkward, so I use N. N means 1, 2, 3, 4, and so on. Whole number and greater than 0. So we can define order property using positive whole numbers. Positive whole numbers. Okay, all right. Yeah, I could have used positive whole numbers instead of natural numbers. Okay, all right. Under this, you have a linearly ordered set. Both to the right and left, we have well-ordered progression here to the right and also to the left. But put everything together, then it's not well-ordered. So the definition of ordering in W is like this, using the set theory. But for integers, we did subtraction, which is well defined here. We did the arithmetic operations here, well defined, we saw that. So we can do the subtraction because we established in 1.7, and that belongs to a W plus. That's how we define it. And Q and R are linearly ordered too. Again, where we're going to define the ordering by subtracting and putting those into the positive integers and positive rational numbers respectively. Here I can use positive integer expression here because we are using Q now. We are talking about Q now, so integers exist. Still, it will be a bit better if I use W plus. So fraction A over B is greater than fraction C over D. You can re-express it using multiplication only, which is well defined in whole numbers. And then greater than equal. In that case, 0 is possibilities, so entire whole number, here positive whole numbers only. And basic idea is that subtract one from the other, and then that fraction is greater than 0, and that means that multiplication is positive. Same goes to non-negative. And then for order relation in R, we take the limit minus limit, use a limit rule, and limit of the difference is greater than 0 or versus greater than or equal to 0. So limit rule applies. And C is not linearly ordered, not even partially ordered, so I don't have to worry about the order properties there. You'll all remember the order properties. Excuse me. You'll all have to remember the order properties, but how to define orders, that's a bit too tricky. So if you forget about those, that's fine with me. Okay, so much for section 1, and we're going to discuss section 2 in a separate video.